Hey everybody. Alright, so we're moving forward in chapter 15, which is about aromatic reactions. And what's the kind of reaction that we were seeing? It had three letters. EAS, right? Electrophilic, aromatic, substitution. Okay, so the two examples we gave last time were and these are just like generally speaking halogenation, so we're going to do bromation and chlorination. Basically you'd have like Br2 iron tribromide, FeBr3, and the thing is that the Br2 and the FeBr3 would pre-react kind of, or coordinate. They're like talking to each other and make this super electrophilic complex, or super electrophile complex. And then the benzene attacks. Basically that gives you FeBr4 minus and FeBr3 and Br minus. Those kind of equilibrate. But you de-aromatize and form this carbocation, and then a base, which could be bromine, Br minus, or some negatively charged thing, takes off the neighboring proton and pushes electrons to re-aromatize. So it de-aromatizes and it re-aromatizes. That's a standard EAS reaction. Okay? And then chlorination, we did the same exact thing. So it's benzene, chlorine, FeCl3. Benzene attacks the super electrophile complex between Cl2 and FeCl3. Make the carbocation. Cl minus takes off the proton, because the carbon that has the chlorine also has a proton, and the neighboring carbon has a plus charge. Okay? Alright, so let's keep going. Okay, so number 9 is a couple other ones. More EAS reactions. Nitration. And sulfation. Or sulfonation. Sulfonation, which makes a sulfur-containing functional group. Alright, and these have the same kind of behavior where we're going to make a super electrophile and then attack it. Alright, so for nitration, let's first do nitration. We have benzene. The reagents to do nitration are HNO3, H2SO4. So we're using nitric acid and sulfuric acid. Actually, yeah, that works. And then you get a nitro functional group, a nitrobenzene. And of course the NO2 group is, the structure of that is N double bond O, O minus, plus charge on nitrogen. So that's what that NO2 functional group looks like. It's N double bond O, single bond O minus, nitrogen's plus charge, oxygen is negative charge. And this is called a nitro group. Okay. Cool. Alright, so what's the mechanism? The big thing is we have to somehow create a super electrophile. We make a super electrophile, then the benzene attacks a super electrophile. So that's the trick, is how do we generate the super electrophile? So for nitration, what you do is you draw nitric acid. I would recommend drawing this exactly the way I'm drawing it. So we have nitric acid. What's the charge on nitrogen? It's positive, right? So we have nitric acid. And then what we have is sulfuric acid, which is HOS, double bond O, double bond O. Okay? And what we're going to do is just protonate this second oxygen on the right using sulfuric acid. Just grab that proton. Okay. of course, you could protonate the other oxygen. You could probably even protonate the top oxygen. But by doing it this way, it lets us get to where we want to go really easily. So that's why I do that. Okay, so we grab a proton. Now what do we got? OH2 plus, right? Like water as a potential leaving group. Okay, so we have O minus, N double bond O plus charge, because nitrogen has 4 bonds to it, and that makes it positive, right? We have water, which could be a potential leaving group. So now, with the left O minus, I'm just going to kick in and kick off water. So, kick off our good leaving group. And now we have this stuff called nitronium. Nitronium, and that's our super electrophile. That's our super electrophile. Okay, so what does benzene do to our super electrophile? Now I'm going to redraw benzene in the same orientation as it was above, with just the way the double bonds are arranged. It's good to keep it consistent. Okay, and we're putting the nitro on the top right. Okay, so now I guess what I got to do is sort of have this bond come attack, just the way I'm drawing it. And that super electrophile loves to be attacked, and benzene is able to attack it, and then that kicks electrons like up. Okay. Alright, so what does that give us? So now the benzene is attached to the nitro. Okay, and kind of looks like that. And double bond O minus. Alright, so what things do I have to draw here? What do I have to draw on my benzene? Well, what things did not change? Oh yeah, where's the plus charge? Plus charge is still on nitrogen. So based on the way I drew this, what do I have to draw here? Well, I got 2 double bonds, right? Double bond, double bond. Now what other things are like on this carbon and this carbon? That's what you have to think about. It's like, what's on there and what's on there? Well, initially we had H's all around, and we still have H's all around. So there's an H up here. And where is, what else should I draw on this bottom right carbon? When the double bond attacks the nitro, what does that leave? A positive charge. Okay, so now how do I finish off the mechanism to make nitrobenzene? What's the difference? Looks like we have to get rid of the proton, and then that regenerates the double bond. So what I usually do here is just say OH2 or some mild base, water that's around. Sometimes I just say B dot dot for base, whatever. Water should be around when nitric acid and sulfuric acid is around, so we always got a little bit of water. Okay, so yeah, it takes the proton, and just like always, we de-aromatize, then we re-aromatize. Okay, cool. That's nitration. Sulfonation is very similar. It's maybe even easier. So the first thing about sulfonation that I'm going to mention is actually, let's draw the. I'll step through the mechanism real quick. Sulfonation. So start with my benzene. Keep the benzene consistent. So to attach sulfuric acid, essentially, the mechanism is for sulfonation is SO3, sulfur trioxide, SO3, and H2SO4. H2SO4. So it's going to be sulfur trioxide, and sulfuric acid. And what you get is a functional group you may have never seen before. It's called a sulfonic acid. Sulfonic acid. It's like a funny carboxylic acid. Sulfonic acid. Highly acidic, low pKa, because if you take off the proton, there's a lot of stabilization and resonance and stuff, right? Okay, so what is the mechanism of this reaction? It's really easy. You know, there are all these EAS reactions, EAS for electrophilic, aromatic, substitution. And so what you got is the benzene, and you react it with sulfur trioxide. All of the other reactions we just did, like nitration and bromination and chlorination, it's like you had to do something to make a super electrophile, right? A super electrophile. Well, this one, it's cool because it already is a super electrophile. There's nothing to do. So this is a super E+. This is a super electrophile already, so the benzene just attacks it. Makes it easy, huh? So the benzene just attacks this sulfur trioxide, which is a super electrophile. Now you got S double bond O, O minus. You got an H still, double bond, plus charge, right? Okay. And now it's like there's two things that happen to give the final product. Base takes the proton and does what? Base, a mild base, takes the proton and re-aromatizes, like always, re-aromatizes. And what's the other thing that happens? Well, you need to somehow protonate the O minus, and we got sulfuric acid around, which is very acidic, and we just grab a proton from there. So grab a proton off sulfuric acid, and we got our sulfonic acid, and we're done with this mechanism. So that is another EAS reaction. Alright. There's one more little tidbit about sulfonation that I'm just going to mention, is that you can totally, if we imagine benzene, we can kind of reversibly form the sulfonic acid. Meaning, I can go one direction or I can go the other direction. So I can actually put it on, and how do we put it on? Well, we just learned it, right? It's what are the reagents to put it on? It's SO3, H2SO4, right? SO3, H2SO4. Okay. And how do we take it off? So you can actually remove it with H3O plus and heat. So the mechanism to take it off is actually almost the exact opposite as putting it on. So like if we had the sulfonic acid and we were trying to take it off using acid, it would be kind of like the opposite sequence of reactions, right? First you would remove this proton from the OH, that would make the O minus. And then the other thing is you would kind of donate a proton with acid, which would generate this intermediate. It's a little hard to see, but there's a homework problem where you can try to do this. And then it's like you get to this step. You get to this step, and then SO3 just breaks off. And that's kind of like how the mechanism might look from sulfonic acid to benzene. Again, you might see a homework problem on that mechanism. You can try that. Okay? One more thing, just thinking about what we've learned in Organic 1, Organic 2. Whenever we have had a reaction where we can like do something and then like do something to put something on and then do something to take it off, where has that been used? Think of Organic 1, Chapter 9, and it was that idea of protecting groups. Remember protecting groups? So what we're going to do is we're going to see this as a protecting group strategy on benzenes, I think next chapter. So just keep that in the back of your mind, is that sulfonic acids, a sulfonic acid can protect a benzene. They can protect a benzene, right? It's going to be kind of cool. So we're going to see this again in the context of protecting group chemistry, alright? Alright, so that's sulfonic acid stuff. Cool. And the reaction was sulfonation of a benzene, and the other one we learned was nitration. So we'll see nitration of a benzene, nitration, and sulfonation. Okay, so far we've done chlorination, bromination, nitration, and sulfonation. Let's keep going. Next reaction, next EAS reaction, because they're all EAS reactions. We all have a similar kind of mechanism. It's called alkylation. Alkylation. What do you think that does? Alkylation of a benzene. Maybe it attaches an alkyl group, right? It attaches an alkyl group. That's exactly what it does. And this was generated or developed by I think two chemists. I think it's two chemists, Friedel and Crafts. And so sometimes we call this reaction the Friedel-Crafts alkylation. Friedel-Crafts alkylation. Okay, so what do you think it does? It attaches an alkyl group. And what mechanism do you think it uses? EAS. So it's just another EAS reaction. Let's show an example. Okay, so I'm going to draw my benzene this way with the two double bonds on the left and the third one kind of going up and down on the right. And we'll show the example of attaching an isopropyl group. An isopropyl group to a benzene. Alright? It's an EAS reaction. So what do you think my reagent's going to be? Well, maybe it contains a isopropyl, right? So something with isopropyl, yeah. And so it's isopropyl and then a halogen like bromine, for example. And a metal. So it's AlBr3. AlBr3. And what was the other metal we saw in this chapter? We saw aluminum, and then we also saw AlBr3. What did we see for bromination and chlorination? It wasn't aluminum, it was iron, right? Iron bromide or iron chloride. So this is like the other metal that we see in this chapter. Okay, so like always, the first thing we got to do is make a super electrophile, right? So the question is, how are these going to react in a way that makes a super electrophile that benzene can come attack? And there's always a little bit of a trick, and this trick is pretty easy. So we draw our bromide, isopropyl bromide, and this trick kind of looks like the initial trick we used for chlorination and bromination. So the alkyl halide, isopropyl bromide, and then the aluminum tribromide kind of interact, and it's sort of like almost like a Lewis acid, Lewis base complex, because the bromine has a bunch of lone pairs, right? And then the aluminum has like a empty p orbital, right? It's like an empty p orbital. So it's like we have a electron donor, electron acceptor, and then the way I do this reaction, these are kind of talking. So the bromine's kind of talking to the aluminum, and it's like it has a lone pair of electrons. It's kind of interacting with the empty p orbital on the aluminum. And then what happens, they're talking, and then the bond just jumps. The bond jumps from carbon-bromine to bromine-aluminum, and that now a pair of electrons jumps. Okay, and what does that give us? A carbocation, right? Because the bond's gone now. Now it's left with a carbocation, and that's our super electrophile. Super electrophile. So in each of these things, each of these reactions, you have a event that leads to a super electrophile. And now, what is the benzene going to do when it sees a super electrophile? It attacks it. So it attacks the carbocation, right? Now it's just plain old EAS stuff. EAS, blah blah blah, dot dot dot. It's just going to be the remaining EAS reaction. So now we got, what do we draw here? How do we draw this thing? So again, what did not change? The left double bonds did not change. And we're putting the isopropyl on the top right carbon. Carbon, carbon, carbon. What else is on like that carbon? Initially we had C6H6, right? C6 carbons, 6 hydrogens. Of course the H is still there. And where's the plus charge? Because when this attacks, we have to create a plus charge, and the plus charge is right here. Okay, and how do we finish the reaction up? How do we always finish these reactions up? Some base takes the proton and regenerates the double bond. What's our base? Well, there's some Br minus around Br minus, right? Because this is also, when this falls off, this kind of regenerates Br minus. So yeah, I just dropped maybe Br minus as our base. Grabs the proton, regenerates the double bond. Okay, so we de-aromatize and we re-aromatize, and that's the Friedel-Crafts alkylation. Okay. A thing about the Friedel-Crafts alkylation is it's typically low yielding. It's typically low yielding, meaning the yield is low. Okay, so it's sometimes you get like a 20% yield. It's not necessarily the best reaction in terms of yield. We'll see a solution to that. Often you have an impurity. Often we have an impurity which might be like, you know, what do we want the reaction to make? We want it to make isopropyl benzene, right? We want to make this, but an impurity that you might see would be like diisopropyl benzene, and that's a problem, right? It's like annoying because we want to make this, but we make some of this, and so there's going to be some solutions to this problem. This is actually kind of a major topic of the next chapter, ch16. So we're going to see a lot of, we're going to talk about this a lot more like in the next chapter. But for now, what can you just take away from this? You know, the Friedel-Crafts alkylation sometimes has some impurities and the yield's a little low, but nevertheless, it is a known reaction. I'll say improvement in a second. Improvement in a second. So I'll explain one way to solve some of the yield problems in the Friedel-Crafts alkylation reaction. Okay, so and then yeah, let me show one more problem. This is one problem. One problem is sort of the yield. Let me show another problem in the Friedel-Crafts alkylation reaction. So another problem. In the Friedel-Crafts, FC, Friedel-Crafts Alkylation. Okay, so say we're doing another reaction. We have benzene, and we're going to react with 1-chloropropane. 1-chloropropane. What's the reagent? What's the other reagent? It's not just this, but we need something else. What's the other thing? Maybe it's a metal with 3 chlorines on it. Is it iron trichloride or is it aluminum trichloride? And the answer is aluminum. It's AlCl3. We use iron trichloride in like the chlorination of the benzene. For Friedel-Crafts, it's aluminum. Okay, so alright, so what's the product? What's the anticipated product, right? Well, this plus this should make what? That, right? And the problem is, no. You don't. You might make some of this, but it's a very low yield of this. You don't actually get very much product, and we'll explain why. But interestingly, you get a byproduct, and the byproduct is isopropylbenzene. So we go from normal linear propyl chloride. We don't get that directly connected, but we actually get isopropylbenzene, right? Exclamation point, question mark, right? So that's actually the major product of this reaction. And why is that? Why do we actually get this and not this? I mean, you know, this looks like the obvious product. Okay, so let's do the mechanism. I'll give you a hint. What was the intermediate? The super electrophile intermediate? It was a something cation. Remember carbocation, and carbocations can kind of rearrange and do some weird stuff. That you know from Organic 1. So we're going to actually dig into your Organic 1 knowledge a little bit. Okay, so the way this works. Remember what was the mechanism? The mechanism was like this reacts with this, and then like you generate a carbocation, right? We just saw that a second ago. It's like these kind of interact, and then the chlorine falls off, and you get a carbocation. But from Organic 1, you should remember that some carbocations are super, super, super unhappy, right? Some carbocations are super, super happy. You have happy carbocations, you have unhappy carbocations. So what are the happy ones? Like happy carbocations would be like a tertiary carbocation, right? Right. So like a tertiary carbocation would be like this, right? Or a secondary. Those are okay. But the worst ones are primary. Primary carbocations and methyl carbocations are so unhappy that they don't like to form. So the main carbocations that are okay are like tertiary and secondary. But a primary carbocation or a methyl carbocation are actually almost like forbidden. Okay, so now you can see why this doesn't want to make a carbocation. This does not want to make a carbocation, and therefore this doesn't want to form, right? Okay, and then somehow it's going to rearrange and you're going to get this. Alright, so how does this all happen now? Let's redraw the propyl chloride, and we're going to have it sort of talking to the aluminum trichloride, like always. So there's this interaction. It's like a Lewis base, Lewis acid interaction. You cannot directly form a carbocation. We can't just say like how the bond jump, because that would make a primary carbocation. And primary carbocations are not good, right? So what happens, and this is actually all kind of out of chapter 6 or 7 maybe, chapter 7, we learned that some weird things can happen. Things can rearrange in a way that avoids a primary carbocation but generates a secondary carbocation. And that's what's going to happen. Is essentially we're just going to draw the H. All right. This was initially discussed in 7 or no, 9. I'm sorry. 9. Where you learned about carbocation rearrangements, which I think was chapter 9. I can't remember now. I think it's chapter 9. But anyway, what's going to happen? We need to make a secondary carbocation. So we need to make this. And how is it going to do that? So what's going to happen is the H is going to jump. The bond is going to break and form AlCl4 minus, AlCl4 minus. And what happens when this hydride jumps? What does it generate? Ah, a carbocation, right? And at this point, I'm going to abbreviate this. Just, you know, it's the same thing as always. Benzene attacks. Let's draw the benzene in the right consistent configuration. Double bond attacks. And then we have a second step, minus proton, and you get the isopropyl benzene. Okay? So, this is a problem. Because what if we want to make this? How do we really need this? Is like for our cancer drug. We need like propyl benzene. Can't make it because with a Friedel-Crafts alkylation because you get this weird carbocation like rearrangement to make isopropyl carbocation, or I don't even know how to name that. Maybe isopropyl carbocation. It's a carbocation with the plus charge on the second carbon, right? Benzene attacks, and then you get isopropyl benzene. What you did not want. We want this, we got this, and that is a problem. Okay, so now the solution. Now a solution. Okay, so what's the solution? What's the solution? Last reaction for this chapter, and then we go into chapter 16. So this is one more Eas reaction. This one is called acylation. Acylation, and it's also a Friedel-Crafts reaction. So we got alkylation, we just learned about, which is Friedel-Crafts, and then we have acylation, Friedel-Crafts. What does acylation mean, do you think? Probably have no idea. Acylation basically means forming a ketone. So the acyl means like a ketone or acetyl-bundo. It's like we're going to install a ketone on a benzene, basically. That's what acylation is. And that's going to solve some of the weird problems with alkylation. So, in a nutshell, we got benzene. We're going to have this method that installs basically a ketone. We're going to have a method that basically installs a ketone onto the molecule. And assuming it's identical to the last reaction we saw, then what are we going to write? Maybe it's going to look like this with a chlorine on it, right? That with a chlorine on it. And that's exactly it. So it's this. How many carbons is it? It's 1, 2, 3. So 1, 2, 3. Okay. Weird a different functional group. You've never seen that before, probably. What's the metal we use for Friedel-Crafts? Something Cl3. It's AlCl3. Okay, so it's basically going to be identical to the Friedel-Crafts alkylation, and this is called Friedel-Crafts Isolation, and the mechanism is basically all the same too. So, but there's going to be a neat thing, and essentially carbocations don't rearrange. The whole carbocation rearrangement business, the hydride shift that we saw, that does not happen for acylation, and that's why it's cool. Okay. All right. So, what's the mechanism? Well, it's the same exact mechanism. So, oh yeah, what's this thing called? This thing, this functional group. What do you think it's called? That's a ketone, right? This is a ketone. This is not a ketone. This is it's called an acid chloride. Acid chloride. We're going to learn lots about acid chlorides later in the course. This functional group where it's C-double-bond-O and a Cl. That combination of atoms is called an acid chloride. Okay, so the mechanism is identical to the Friedel-Crafts alkylation. So we're just going to redraw the acid chloride backwards. And what's going to happen when it sees AlCl3? Well, we also, same thing, we got electrons in around the chlorine and absence of electrons around the aluminum because there's almost like a free p orbital. So you got an open p orbital. We can say that this is a Lewis base. This is a Lewis acid. So these two things are kind of talking, and the way I show talking is I show a little dot 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 dot. Okay, so they're talking, and there's kind of like forming a complex, and then all of a sudden the bond jumps. The bond, the C-Cl bond, the carbon-chlorine bond jumps, just like it did in the alkylation reaction. Alright, and what does that make? Well, it makes AlCl4 minus. That's not the exciting thing, though. The exciting thing is this, with a what charge on it now? It's if chlorine goes away, what's the charge on that thing? And the charge is now plus charge. Plus charge on the carbon, right? Because chlorine goes away, takes its electrons with it, and so now we make it's actually linear now. Let's draw it better. How many carbons is it? It's 3 carbons, so it's this, right? 1, 2, 3 carbons. 3 carbons, right? 1, 2, 3. Now what's the charge on the carbon? What's the charge on this carbon? Well, if the chlorine went away and took its electrons with it, it's a plus charge. So you could say this is a carbocation, right? It's a carbocation. Now, is this just any old carbocation? It looks like a little weird of a carbocation. You haven't seen this kind of carbocation before. But it is just it's a carbocation with a double bond O on it. And it is electrophilic, so the benzene can just attack it, right? So the benzene can just attack this. But what's interesting is this is actually, it's got a little bit of resonance. The oxygen can kick in, and that actually stabilizes it. And being stabilized, that's a reason this doesn't rearrange. This doesn't like change its structure. You know how we saw, you know, like a secondary or primary, secondary, tertiary carbocations, how they can rearrange, and like secondary might become a tertiary carbocation, etc. Well, this is stabilized. This is a I'll draw the resonance structure. This is a stabilized carbocation. Stabilized carbocation, right? It's a stabilized carbocation. It's actually stabilized by what? What's this thing we're drawing? And what does it look like? It's weird. Isn't that weird? If the oxygen kicks in, now you have a triple bond oxygen, right? And where is the charge now? It's not on the carbon, but the oxygen, right? Okay. So this is a stabilized system. It's stabilized by what? What's this thing that we're drawing here? It's resonance. Resonance. And we see this over and over and over in organic too, where things are stabilized by resonance. Particularly a carbocation. It's a carbocation that's stabilized by resonance. We see this so much that we even give it a name. We're going to call it an RSCC. RSCC. So, about 1,000 more times in this course I'm going to say, what is this carbocation that's stabilized with resonance? And you're going to say, oh, and I'll say it's four letters, and you're going to say, what are the four letters? It's RSCC, resonance stabilized carbocation, okay? Okay, this is the super electrophile though. Super electrophile. So now the benzene just attacks, and that gives us our product. And I'm going to abbreviate that. I'll just draw benzene over here. You can draw that out if you like. But the benzene, basically what happens is the benzene attacks this carbon and kicks the electrons back onto the oxygen. So the benzene attacks the carbon, kicks the electrons back on the oxygen. This is Eas. That gives you the ketone. Of course there's a second step. What is the second step? The second step, of course, after the benzene attacks, the benzene becomes a carbocation. It's actually, technically, that's an RSCC too. It's a resonance stabilized carbocation. But if I was asking you for the mechanism of this, you would need to draw that second step also. And if you need guidance, look at the last couple of problems or reactions. We've talked about this a bunch of times. Benzene attacks. That makes a intermediate de-aromatized compound, and then that loses a proton, and then it gives you the product. Okay. All right. Cool. So one more thing. This RSCC has another name. It's called. This resonance stabilized carbocation is also called acylium. Acylium ion. So it has another name for that arrangement. All right, cool. And the yield is great. It's like 68–80%. So this is a very well-behaved reaction. Unlike the Friedel-Crafts Isolation, which the yield was like 20% or something like that, right? Okay. All right. So let's go back a bit now. How does this solve the problem that we were having previously? Because the problem previously was I wanted to do alkylation. Let's go back to the last page real quick. The alkylation, remember this? The problem was like we want to make that. Well, we got that. So how does the acylation solve this problem? Because the acylation makes a ketone, but what if we want the alkane, right? The CH2, CH2, CH3. How can we modify the acylation reaction so that we can make this? Because we need this for our project. We need propylbenzene, right? Okay, so I'll just say at the bottom of this page of the acylation reaction. as I'll say, what if we really need propylbenzene? What if we really need propylbenzene? This doesn't really help us because we're making a ketone, right? We can make ketones till the cows come home, but that's not what we want. We want it without the ketone. Fortunately, there's a way to remove the ketone. Okay, so what we do a Friedel-Crafts Isolation, which makes a ketone. Acylation, acyl is ketone, and then reduce the ketone off. Then we can reduce the ketone off. So the solution is basically we're going to take benzene, do the Friedel-Crafts Isolation, AlCl3. That makes the propyl ketone. And then, new reaction, we're not going to talk about a mechanism, but if a ketone is right next to a benzene, we can just wipe it off with H2 palladium on carbon. So that gives us what we need, what we were set out to make earlier. So we can take the ketone and wipe it off with H2 palladium on carbon to make the desired propylbenzene product. No mechanism for this one. Occasionally we'll just totally skip mechanisms, so no mechanism for this one. The only other thing is that in order for this to happen, for this H2 palladium to kick off a ketone like this, you need the benzene. You need the benzene, okay? If you don't get the benzene, this doesn't do anything. So I'll just show this in the very bottom here. Like if I have cyclohexanone. Cyclohexanone is just a ketone, right? And I do H2 palladium on carbon. H2 palladium on carbon. Does that make cyclohexane? Is the question. And of course it does not, because there's no benzene. You would need a benzene next to the ketone. So this is a NR. No reaction. X. Cannot do this. Cannot take cyclohexanone and make cyclohexane this way. Alright. We will learn ways to do this, to take an arbitrary ketone and wipe it off. It's just you can't use H2 palladium on carbon unless you got a benzene next door. Alright. Alright, we're on to the next chapter. So the last thing we talked about was the Friedel-Crafts Isolation, and that was the last reaction of 15. So now, let's enter chapter 16, which is kind of a continuation of 15. More aromatic reactions. So now it's going to be EAS, which of course is that common mechanism we talked about a bunch, of substituted benzene derivatives. EAS of substituted benzene derivatives. So meaning that all that means is it's the same exact stuff as 15 we just talked about, but we're going to start with benzenes that already have stuff on them, and that's going to, be another little twist on this theme. So a little overview. Recall the Eas mechanism generally. What was the Eas mechanism in a nutshell? So it was like benzene. We had a super electrophile, E+. It was usually super. Somehow it was super electrophile. And then somehow this would attack the super electrophile. And then you get E, you get H, you get a plus charge, double bond, some kind of base would do what? to this thing, it would take the proton, you would get your electrophile attached. Okay, all right. So that was what we saw 1,000 times last chapter, right? Benzene attacks super electrophile, base takes proton, and you regenerate the benzene. Okay, so what's going to happen now in this chapter? So what's going to happen now? There's going to be kind of two situations, and we're going to overview this, and then we're going to go into lots of detail. But the first situation will be if you got an X already on a benzene. You have an X group on a benzene, and we react with electrophiles again, super electrophiles. Assuming X is an electron donating group, and we'll show those in a second. Assuming X is an electron donating group, and what's going to happen is you're going to get that electrophile in two different places. The para position, and the ortho position. Para position and ortho position. Okay? And we're going to say that X is an ortho-para director. X, of course, which is an electron donating group, is an ortho-para director because it's directing E to go to the ortho and para position. Ortho-para. So what are some X groups that do this? Methyl, CH3. Methoxy, OCH3. Alright, there's a couple. Nitrogens, NH2. We'll say NHR, which kind of means nitrogen with a hydrogen and then some kind of R group. Just like, you know, variations of this general theme, nitrogens, etc. Okay. In general, all of these things have lone pairs. Right? Except CH3 does not have a lone pair, but it still acts kind of in this donating group type of thing. Okay? Alright, so what do you think happens when we do the same exact thing but X is an electron withdrawing group? EWG, electron withdrawing group. So donating groups kind of donate electrons into the ring from the X group inward. A withdrawing group is kind of pulling electrons away from the benzene onto the X group. It's an electron withdrawing group. So if these are ortho-para directors, what do you think this is going to be? Where do you think E is going to go now? Ortho-para. Now, with electron withdrawing groups, E gets directed to the meta position. And then we say that meta is a meta-director. Meta-director. Cool. Okay. So then real quickly, in a nutshell, what are some electron withdrawing groups that cause meta-direction? And most of these things are like C double bond O, like a aldehyde. You can kind of imagine that, right? Like, if this is on the benzene, the squiggly means it's on the benzene, it can kind of suck electrons towards it and up onto the oxygen. There's going to be a lot of examples like that. What other C double bond O things? You have aldehydes, you got ketones, you got esters, you got carboxylic acids. Anything else? Anything else? All these C double bond O things. C triple bond N, which is a nitrile. Remember nitrile? Functional group. Nitrile is a functional group. Yeah, that's kind of like that. Nitro does this. Remember nitro? We just learned about it last chapter. Nitro, right? It does this. What else? Sulfonic acids, which you also learned about last chapter. Anything that has kind of like a atom and then that double bond to O or N, all of these do this. They're in the meta directory category. Sulfonic acid. One other interesting one that's a little different than all of these, that's CF3. CF3, trifluoromethyl, which is pulling electrons towards the fluorines, so it is electron withdrawing, because it's sucking electrons from the benzene, and the benzene is assumed to be attached at the squiggly line. So this is also an electron withdrawing group. All of these are considered electron withdrawing groups. All of them are meta-directors. Okay? So part of what you're going to need to do is learn, you know, maybe on an index card or something, like what are all the electron withdrawing groups, and you know, they're all meta-directors. And these kind of things are all electron donating groups, and they are ortho-para-directors. Interestingly, and I'll mention this, like chlorine, it also has lone pairs. Chlorine, bromine, etc. They are also in this ortho-para-director category, but they're going to be a little different, a little bit weird, so I'll put a parenthesis around them. Okay. Alright, so there's two main things we've got to talk about. Two main things to consider initially, and then there's a little bit more in this chapter. Two main things. First thing, as you might imagine, is this whole ortho-para direction versus meta-direction. It's like wider things ortho-para directors, wider things meta-directors. That's one thing we have to talk about. The other thing, and we'll ignore this a little bit until later, but there's a concept called activation versus deactivation. Activation versus deactivation. So, in a nutshell, some benzenes, it's like you have things on them, and those things are like will speed up the reaction with electrophiles, and those are going to be called activators. So it's like the rate of the reaction is going to be increased, activation. And other things are going to maybe pull electrons away from the benzene, and they're going to be called deactivators. Anyway, there's ortho-para direction and meta-direction is one thing we got to talk about, and then we'll talk about this concept called activation and deactivation. They're kind of independent, so, yeah, I don't know, sort of. There's some intricacies we have to talk about. All right, so I also will point out that these are explained in opposite order than the textbook. So if you're reading the textbook, which is always good, and you should totally read the textbook, I think they first talk about activation, deactivation, and then ortho-para direction versus meta-direction. But I think, to me, it makes more sense to first do the direction stuff. Okay, both of these concepts, direction versus activation, deactivation, both are explained by an interplay of two kind of electronic effects on the benzene. Okay, so the first one is, let's see, first effect, I guess, is induction effects. The second is resonance effects. So you know a little bit about these effects. You probably know more about resonance than maybe more. You've heard more about resonance than induction. But what are these two effects in a nutshell? So resonance deals with pi electrons, not sigma. Resonance, which you know about resonance, right? Pi system, pi electrons, right? Induction deals with sigma electrons. Okay? So, and these are ways molecules transmit electron density from one atom to another atom. Inductive effects and resonance effects. So, let's draw these out and briefly. Let's think about methylbenzene. Methylbenzene, right? And let's think about trifluoromethylbenzene, which we've talked about these just a second ago, CF3. I mentioned that this is an ortho-para director, this is a meta director, but that's not what I care about this second. The big thing is, like, what is the methyl doing here and what's the trifluoromethyl doing here? And how does that relate to what we're calling induction effects through the sigma system? Well, the methyl can kind of donate its electron density downward. It's got three hydrogens, and they have electrons. Okay, the fluorines though are pulling electrons away because fluorines are electronegative, right? So this is kind of donating inductively in the inductive system, and this is withdrawing. So this is like donating in, this is sucking electrons away from the benzene. Resonance effects are through the pi system. So let's just draw those in a nutshell. I'll do it underneath here. OCH3. And by pi system, what kind of bonds are pi bonds? Where did we learn about pi bonds? Like alkenes and alkynes, right? Double bonds, right? Anyway, in a nutshell, you can imagine this can kind of push electrons down to make what kind of bond is that? We have a single bond and we add a second bond. It's almost like a double bond. It's like double bond character, right? So that's kind of an example of resonance effects through the pi system. And this is donating. This is donating through the pi system. These are sigma interactions, and this is like a pi interaction. And what's the opposite? What's the opposite? So if we have, just as an example, I don't know, aldehyde. Okay, this can pull electrons towards it. Okay, so this double bond here can pull electrons from the benzene to make kind of a double bond there, break this, make another double bond. Okay, so in a nutshell, we got right here, we have kind of, these are inductive effects, examples of inductive effects, these are examples of resonance effects. Methyl is donating by induction, right? Methyl is donating by induction. Trifluoromethyl is withdrawing by induction. Methoxy, OCH3, is donating by resonance to make a pi bond. And aldehyde is kind of withdrawing by resonance and kind of pulling electrons through the pi system. So if you get these, this is a good start to learn everything else in the chapter. All right? Inductive effects, donating, withdrawing. Resonance effects, donating, withdrawing. Alright, so that was all number one, overview. Now we're on number two. And the main topic for number two is that electron donating groups, generally, what do we say? Are they ortho-para or meta directors? They are typically ortho-para directors. I already said that, and here we are saying it again. And we'll go into why. Why are electron donating groups orthopair directors. So first let's list an examples of them, and I'm going to give myself a big page because there's a bunch of them. Examples of orthopair directors. We already saw some. Methyl, we'll say, or alkyl. So this could be methyl, ethyl, whatever. There are other alkyl ones do the same thing. And this is an electron donating group by induction or resonance. Is it donating electrons through induction or resonance? Well, it can't form double bonds. There's like the H's and the carbon can't form double bonds, so this is not resonance, this is induction. So induction, is that the sigma bonds or the pi bonds? This is sigma, right? Sigma electrons, right? Okay. Next, we got a bunch of resonance ones. OCH3, NH2, amide, so it's like NH and then like acetyl bond O, CH3. It's an amide functional group. Yeah, these are examples now. They're electron donating group by induction or resonance. They all got a lone pair on them that can kind of kick in and make a double bond like resonance style. So all of these are electron donating group by resonance. And is that sigma or pi electrons? It's pi, okay? So far so good. So these are all orthopair directors. We'll explain why they're orthopair directors in a second. But I need to mention a third category now, which are chlorine and bromine, for example. These are a little funny because they got lone pairs on them too. Alright, so that would make, if they have lone pairs, that would make them, are they donating groups by resonance? And the answer is yes, they are donating groups by resonance. EDG by resonance. But why are they a different category? It's like the same thing, right? What's different about these guys? So the funny thing about halogens, chlorine and bromine, are the main ones we talk about. They are donating by resonance, but they are actually withdrawing groups by induction. And we're going to come back to that. So they donate by resonance, which is the pi system, and they withdraw by the sigma system. So they're pushing one way and pulling another way. Totally weird. Chemistry's weird, right? And the main thing, the main takeaway, and I'll just give you a preview, is that these are going to be orthopair directors. All these are orthopair directors. Every one of these are orthopair directors. But these are going to be activators, orthopair directors, and they're going to be activators. And we'll talk about activation again later. These are orthopair directors and they're deactivators. And that's just all that's going to mean is they'll slow down the rate of the reaction a bit. These kind of speed up the rate of the reaction. Okay? Keep that in the back of your mind, that halogens are electron donating groups by resonance and electron withdrawing groups by induction. Alright. Alright, so what I want to do is, just lastly for today's lecture, I just want to kind of explain why these are orthopair directors, why all of these are orthopair directors, and do it kind of mechanistically. Alright, so the way to explain why they're orthopair directors is we're going to do this by talking about explained by the carbocation intermediate of the Eas reaction. So we need to talk about that carbocation thing. So we need a little bit of space on the page. I'm going to try to squeeze it at the bottom of this page. And what I'm going to do is I'm going to draw benzene, with an EDG on there, electron donating group. Alright, so all of the things above are EDGs, electron donating groups. Make sure you draw the benzene this way. It's with the double bond the way I drew it, or the scheme's not going to work out too well. We're going to react this with a generic electrophile E+. Generic electrophile, okay? And there's going to be three outcomes. There's going to be ortho, which I'll draw kind of upward, ortho, para, and meta. Ortho, para, and meta. We're going to deal with each of those kind of individually. Alright? So, what happens when this guy reacts with this and attacks at the ortho position? What do we get? So I'm going to just redraw the molecule. I'm going to say EDG. Get the electrophile, and we got a double bond and a double bond. That's how we drew it, right? And where's the H that we still have? Of course the H is still there. And where is the positive charge? Because there's always a positive charge in these reactions. Ah, there's the positive charge, right? Okay. And, of course, after you lose the proton, and I'm not going to show all this proton removal and everything, just to make this simple. Once the proton is removed, though, what's the product? It's E and EDG, right? Okay. And now I'll ask, do you think this is a happy intermediate? Like, think about the donating group. What do donating groups do? They donate. It's donating electrons in. And you're donating electrons to a carbon with a positive charge, which wants electrons, and I am just going to say star to suggest happiness. It's a happy, happy carbocation. It's a weird asterisk I tried to draw. But anyway, this is good. It's good. It's a favorite intermediate, right? Now para. So this is what happens with para? Assuming the electrophile goes to the para position, so the benzene attacks and puts it in the para position, what do we got now? We got a donating group. Where's the E? Where is it going? Ah, the para position is right here. What else is on that carbon? An H. What other things are in the... What are the other double bonds, right? Well, we got one on the left. Looking back over here, right? We got one right there. We got one right there. And where's our positive charge? It's right here, right? So now the question I have for you is this a happy intermediate? Is there anything like happy about this, or like stable? Well, you have a donating group, and it's donating in, and there's a positive charge. And the answer is you can't actually see it. Here it was obvious, right? Donating group, positive charge, happy, happy, right? But here it's not obvious until you do a resonance of the double bond. And the double bond resonates. What do you got? Resonance down. Ah, you have that same really nice situation. EDG plus charge. So you have to get really good at drawing resonance structures. EH. Ah, same situation. Donating group, positive charge, and it's very happy. Put a little star. Super cool. That explains why we get ortho direction and also why we get para direction. I'm going to wrap up real quick with meta. I just want to finish up meta. So how does this all wind? How do we get to the product here? EDG, E, right? Of course, now the protons are removed, the double bonds shift around, and then you get to the para position. So both of these are really good, right? And that explains why ortho is happy, para is happy. Let's just do meta, which is not happy, and then we'll be done. Okay, so how do we do meta? To draw meta, so for meta we have E, H, EDG, double bond, right? And the positive charge is where there's a positive charge. It's right here, keeping everything consistent with how we started the double bonds, right? Okay, and the question is this favored? And you probably have an idea in your mind, like, no, it's probably not. These are definitely favored, and these are ortho para director. So let's see why it's not favored. Because I'll push my electrons this way. Resonate. We're just push towards the positive charge, right? And now where's the positive charge? It's right here. And you have a double bond, EDG, right? And a double bond, and an H, and an E. Cool. Alright. Is that favored? It's not really favored the way this is favored, where EDG and the plus charge right next to each other. It's not, and this is also favored, but this is not favored the same way. This is not a nice star or a happy face. It's more of a frowny face, right? That's not a favored interaction. And is there another resonance we can draw? Well, yeah, we can push the double bond the other side and put a plus charge over here, right? Is that favored? H and E. Are any of these favored? And it's not. This is not favored, that's not favored, because the donating group is not directly adjacent to the positive charge. So this is also a frowny face. Okay, so we're basically done. What I was trying to show is why electron donating groups are ortho para directors, and I showed that. I could even add little smiley faces, smiley face, to show that that's a favored carbocation, that's a favored carbocation, that's a favored carbocation. Yeah, they're in resonance. These are unfavored carbocations, and that's why donating groups don't make meta products. Donating groups make ortho and para. Alright, so we went a little bit over, but hopefully this makes sense. And when we explain how, meta direction, it's going to be a very similar explanation. Alright, so hopefully we're moving along, alright? And I think we went a little bit over. Alright.